Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome, everyone. Today we are strapping in for a ride that might just completely upend our sense of cosmic orientation. We're asking a question that sounds incredibly fundamental, almost simple. How fast and in what direction is our solar system actually moving through the universe?
It really does seem like a simple question, doesn't it? But the answer is, well, it's anything but. And trying to determine our absolute velocity relative to the most distant things we can see, that's not just some mapping exercise. It's a foundational test for how well we actually understand the very fabric of space-time and, everything that's happened since the Big Bang.
Exactly. We've been looking at some truly fascinating research that zeroes in on measuring this specific velocity. The sources we're analyzing center around a huge study, a landmark study, really, published recently in Physical Review Letters. It was led by an astrophysicist named Lucas Bouma and his team at Bielefeld University.
And our goal here is pretty straightforward. We need to unpack these findings because they deliver a serious, maybe even a fatal blow to one of the bedrock assumptions of the standard model of cosmology. And for you, listening, we have to start with the really staggering conclusion. Based on their analysis of distant galaxies, the solar system is moving, get this, more than 3 times faster than every single existing cosmological model predicts.
3 times faster. That sounds less like a scientific measurement and more like a cosmic speeding ticket. And this isn't some minor calibration error, right? This is a statistical deviation so vast that, I'm quoting Bohm here, it forces the entire scientific community to reconsider our previous assumptions. Assumptions about how the universe is built on the largest scales.
It's a genuine shockwave. And it's a shockwave precisely because it forces this confrontation with the most successful framework we have for understanding the universe. Yeah. I mean, the standard model of cosmology, lambda CDM, is explained pretty much everything, from the proportions of elements in the early universe all the way to the rate of cosmic expansion.
It's the reigning champion of theories.
It is. So when a measurement comes along that contradicts this model and does so with such incredible statistical certainty, scientists can't just ignore it. They can't just sweep it under the rug. They have to fundamentally test the foundations of reality itself.
Okay, let's unpack the groundwork here. Before we get into this new, frankly shocking speed, we need to establish the baseline. Why is pinning down the speed of our solar system so crucial to our cosmological understanding? What's the fundamental principle it's testing?
It's testing something we call the cosmological principle. And this principle is, it is the unshakable foundation of all of modern cosmology. Essentially, it posits 2 things about the universe when you look at it on the grandest scales, past a few hundred million light years or so. It says the universe is both homogeneous and isotropic.
Okay, so homogeneity means it's mostly smooth and uniform, like a giant, perfectly mixed soup, no big lumps.
Exactly, no big lumps. And isotropy means it looks the same in every direction you look. There's no special direction, no preferred axis, no up or down in the cosmos.
No cosmic North Star.
Precisely. And if the universe really is homogeneous and isotropic, it has no center. That means gravity should be pulling more or less equally in all directions on a large enough scale. Our motion, therefore, should be relatively constrained. It should align with the overall flow of cosmic expansion and, the small local gravitational tugs from our immediate cosmic neighborhood. Things like the Virgo supercluster.
I see. So the standard model doesn't just pull a speed out of thin air. It uses this assumption of large-scale uniformity, the cosmological principle, to establish what you could call a cosmic rest frame.
That's the perfect way to put it. The ultimate cosmic rest frame is defined by the cosmic microwave background, or the CMB. This is the faint afterglow radiation left over from the Big Bang. It fills the entire universe. And if you are truly at rest cosmologically, the CMB should look perfectly uniform, the same temperature, no matter where you look.
But we know we are moving relative to the CMB. That's something we've measured for decades, right?
Oh, yeah. We have, yes. And it's one of the great discoveries of modern cosmology. When we look at the CMB with sensitive instruments, we see a tiny but very distinct temperature asymmetry. One side of the sky is ever so slightly hotter, which means it's blue shifted, and the other side is slightly cooler, or redshifted.
This is the famous CMB dipole.
That's the one, and it's a direct measurement. It tells us how fast we, the solar system, are moving relative to the universe's background radiation. And that speed is about 370 kilometers per second.
So that's our expected baseline motion. That's the speed we should be going at because of all the known local gravitational influences and the overall expansion of the universe.
Right.
The standard cosmological model is perfectly happy with that speed.
Correct. It all fits together very neatly. But, and this is the crucial point, this new research wasn't measuring our motion relative to the CMB. It was measuring our motion relative to matter, specifically the distribution of incredibly distant galaxies.
So two different rulers to measure the same thing.
Exactly. The CMB gives us a benchmark for the very early universe, just a few 100,000 years after the Big Bang. But the distribution of distant galaxies, that provides a benchmark for the current large-scale structure of the universe. If the cosmological principle holds, if the universe is truly uniform, these two measurements, our speed relative to the CMB and our speed relative to all that distant matter, they should align. They should give us a very similar velocity.
And this is where the contradiction just slams into you. Lead author Bouma explicitly states his words that this new velocity measurement clearly contradicts expectations based on standard cosmology.
It's so much more than just a deviation. The velocity they measured, based on the actual material distribution of the universe, is statistically forcing us to conclude that we're moving 3 times faster than we should be. And that translates directly into a much, much stronger directional tug. It means that the universe, as defined by where the galaxies are, appears significantly less uniform than the universe as defined by that ancient microwave background light.
Wow. Okay, so this presents a massive problem for the standard model. It suggests that either there is some truly monumental, previously unseen gravitational engine in our local universe that is accelerating us, or
the fundamental assumption that matter is spread out smoothly and uniformly across the cosmos is just wrong.
And that choice between a local gravitational anomaly and a fundamental structural flaw in the universe itself, that's really the entire pivot point of this whole discovery, isn't it?
It is. And we can only really address that choice once we understand how on earth they even made this detection. Because you can't just use a regular telescope when you're looking that far back in time.
That sets the stage perfectly for the technical side. How did they do it? How did they detect the speed? They needed an extremely distant, effectively fixed reference point.
And for that, they chose radio galaxies as their cosmic markers. Now, these are not your average spiral or elliptical galaxies. These are very distant galaxies that are distinguished by these massive jets of particles. They're powered by supermassive black holes at their centers. And these jets emit incredibly powerful radio waves. That's a form of electromagnetic radiation with very, very long wavelengths.
And what is it about radio galaxies that makes them the ideal targets for this kind of measurement, as opposed to, say, using standard optical telescopes like Hubble?
The key advantage is observational depth and penetration. In space, visible light, the kind our eyes see, is easily scattered and blocked. It gets absorbed by cosmic dust, by gas clouds, by all sorts of intervening matter. So optical instruments can only see so far with perfect clarity.
It's like trying to see through cosmic fog.
A perfect analogy. But radio waves, because of their very long wavelengths, can essentially bypass that cosmic fog. They penetrate the interstellar and intergalactic medium far more effectively. They just sail right on through.
So by using radio telescopes, these researchers can see much, much deeper into the cosmic structure. It gives them a vastly larger sample size of objects to establish that universal background reference frame.
Exactly. You're counting objects that are so incredibly far away that their spatial distribution should perfectly reflect that large-scale uniformity that the cosmological principle assumes. You really need billions of these faint sources to achieve the kind of statistical precision required for this measurement.
Okay, so they have their targets, billions of radio galaxies. Now, let's get into the physical mechanism of detection. They aren't tracking a single galaxy over time, like a police radar gun. They're looking at the distribution of all of them.
So how does our solar system's motion translate into a discernible pattern in these light sources? Let's talk about this headwind principle.
Okay, the headwind principle relies on a couple of relativistic effects that are tied to motion. The first is the Doppler effect, which most people are familiar with. The second is something called light aberration.
Let's start with the familiar one then, the Doppler effect. Right, so if you're moving rapidly toward a stationary source of waves, sound or light, doesn't matter, the waves appear compressed to you. They get shifted to higher frequencies. And if you move away, they appear stretched out, shifted to lower frequencies. Think of an ambulance siren.
Right, it gets higher pitched as it comes towards you, lower as it goes away.
Exactly. Now, when you apply that to light, it means objects we're moving toward appear slightly brighter and bluer. That's the higher frequency part. And objects we're moving away from appear slightly dimmer and redder, the lower frequency part. So this introduces a fundamental asymmetry in the intensity of the light we receive from different directions.
That makes sense. But the researchers weren't just measuring the intensity of the light, they were counting the actual number of galaxies. So how does that work?
That's where the second effect, light aberration, comes in. And this is really what the headwind metaphor is all about. Think of it like this. If you're running forward in the rain, even if the rain is coming straight down, more raindrops hit you in the face than on your back.
Okay, I can picture that.
It's a similar idea with light. Our motion through space causes a slight directional bending of the incoming light rays from these distant galaxies. So objects that are actually distributed perfectly uniformly across the sky will appear, statistically, to be slightly more concentrated in the direction of our velocity. We sort of sweep up more of them in our forward view.
So to put it all together, if the solar system is speeding toward the constellation Leo, we will perceive slightly more radio galaxies in that specific direction, a kind of subtle cosmic pileup. And this perceived asymmetry, more galaxies counted in one direction than the opposite, that is the technical signature they're looking for. It's called a dipole anisotropy.
Precisely. It's an anisotropy, a lack of uniformity, that should be caused entirely by our own motion relative to that distant static background. But I really have to stress this again. This difference is absolutely minuscule. It's tiny. If the universe truly adheres to the standard model, this dipole should be incredibly faint. Detecting it requires counting sources in the billions and using instruments of just immense sensitivity.
And to make those extremely sensitive measurements, the team relied on what might be the world's most impressive listening device, the LOFAR telescope, the low-frequency array.
LOFAR is absolutely critical to this discovery. And it's important to understand it's not a single massive dish like you might picture. It's a network of thousands of small antenna stations that are spread out across several countries in Europe, and they're all linked together electronically to act as one giant telescope.
So that distributed nature, having antennas so far apart, that gives them an unparalleled baseline, right? The distance between its farthest components. And that translates to incredible angular resolution.
Incredible resolution and immense sensitivity, especially for detecting these very faint, low-frequency radio waves from the early universe. They could map the distribution of these radio galaxies with a precision that previous single-dish telescopes simply couldn't dream of achieving.
So they took the primary data from LOFAR, and the sources say they combined it with information from 2 additional radio observatories. I assume that's to cross-check their data.
Yes, to ensure their galaxy count was as comprehensive and accurate as possible, to make sure they weren't missing anything. But their challenge wasn't just collecting all this data, it was analyzing it accurately, and that led to a really key part of their work.
This statistical innovation. The sources note that the team needed a new statistical method specifically because many radio galaxies consist of multiple components. Why was that such a big hurdle?
Well, imagine you're trying to count distant streetlights from a satellite. But sometimes a single streetlight isn't just one bulb. Maybe it's a big sign with 2 or 3 separate light bulbs very close together. If your telescope doesn't have the resolution to distinguish them as part of a single sign, you might count 3 lights when you should really only be counting one originating source.
I see. And if you don't account for those multi-component sources correctly, you could artificially inflate or skew your galaxy counts in certain areas of the sky, which would ruin the whole measurement.
Exactly right. Radio galaxies are often these incredibly complex structures. You've got the central core, where the black hole is, and then you have these 2 massive radio lobes, these jets, extending far out into space on either side. The older statistical methods often struggled with this. They would sometimes treat these lobes as separate sources from the core.
So the new statistical method developed by Booma's team was designed to be smarter about that, to recognize that a core and its 2 lobes are all part of one single galaxy.
Yes. It counts for this multi-component nature, ensuring that the team was counting distinct, originating galaxies, rather than just counting the individual bright parts of a single galaxy.
And this methodological rigor is so important because the source material points out something that I found really interesting. This improved analysis yielded measurement uncertainties that were larger but also more realistic.
And that is a huge sign of robust, honest science. When scientists report larger, more realistic uncertainties, it means they've been conservative. It means they have fully acknowledged the inherent imperfections and complexities of measuring this kind of data across vast cosmic distances. They weren't trying to make their data look tidier or more certain than it actually was.
And despite introducing these larger uncertainties, which should make it harder to claim a discovery.
The measured signal was so powerful, so strong, that it still completely defied the standard model's expectations.
And that leads us directly to the statistical weight of this finding. This is where the conversation turns from just methodology to, a genuine discovery. We have to talk about 5 sigma.
Yeah.
Even with the larger, more realistic uncertainties applied by their new statistical method, the deviation from expectation exceeded 5 sigma.
5 sigma is the gold standard of scientific discovery, especially in particle physics and cosmology. To put that into context for you, in many fields, a 3 sigma result is considered pretty interesting. It's evidence of a signal. It makes people pay attention. But 5 sigma means that the probability that this result is just a statistical fluke, some random error in the data that will vanish if you measure it again, is less than 1 in 3.5 million.
1 in 3.5 million. It is the threshold for popping the champagne and shouting, "We found something new!" in physics. Why is such a stringent threshold necessary, particularly in a field like cosmology?
It's because the theories you're testing, like the standard model, are so incredibly successful and so fundamental. If you're going to stand up and claim you found something that fundamentally breaks decades of established physics, you'd better be virtually certain that your instrument or your analysis hasn't somehow misled you. 5 sigma provides that statistical certainty. It's the community's way of saying, okay, this isn't noise. This discrepancy is physically real.
And what exactly is this robust physical discrepancy they found? It's the specific anisotropy, that dipole that we were just discussing.
Right. Their measurement shows that the directional asymmetry in the distribution of all those radio galaxies, the dipole, is quantified as being 3.7 times stronger than what the standard model predicts it should be.
So the measured headwind is 3.7 times stronger than the model allows. And if the strength of that dipole directly correlates with our velocity relative to those distant sources, then our solar system must be traveling 3.7 times faster than the expected cosmological speed. That is the core finding.
That is the core finding. It's not just a small deviation, it's a profound conflict. If the distribution of matter in the universe were truly uniform, and if we were moving at the expected CMB-derived velocity, the dipole that LOFAR measured would be much, much weaker. This excessive strength indicates a velocity that is wholly incompatible with a smooth, uniform universe.
What's so fascinating here, and what makes this so compelling, is that the scientists didn't just stop at their own LOFAR data. They proactively sought independent validation. And that's the critical step that elevates this from just an interesting result to a potential paradigm shift. The paper says the new results confirm earlier observations based on studying quasars.
This step is absolutely non-negotiable for a claim this large. You have to do this. Let's define quasars clearly for everyone. They are the supermassive black holes at the very heart of distant active galaxies. They're in the process of consuming enormous amounts of matter, and as they do, they heat up and emit so much energy that they can outshine their entire host galaxy. They are the brightest beacons in the universe.
So why is the quasar confirmation so important here? What makes it such a powerful piece of evidence?
It's because the earlier studies that found a similar effect were looking at quasars using infrared data. Now think about the difference there. The BOOM study used radio waves, very low frequency, very long wavelength, and focused on radio galaxies, which are defined by their extended jets. The earlier, confirming studies used infrared light, a much higher frequency, shorter wavelength, and focused on the extremely bright, compact central cores of quasars.
So the detection method was entirely different. They were using a different part of the electromagnetic spectrum, and they were measuring completely different types of distant objects. And yet they yielded the same unusual effect.
This is the scientific clincher. It's what makes the results so hard to dismiss. If 2 entirely independent observational techniques using 2 different cosmic marker populations, 2 different spectral bands, and 2 completely different instrument setups, if they both point to the exact same massive, statistically significant directional asymmetry, then the signal is almost certainly genuine.
It's not a fluke in the LOFAR antennas.
Exactly. Yeah. It strongly suggests that this massive velocity they detected is a real feature of our motion through the cosmic matter distribution, and not some weird systematic error in the LOFAR instruments or some peculiar property of how radio galaxies emit light.
And this just moves the conversation entirely away from questioning the instruments and directly to questioning the fundamental laws of cosmology, which leaves us with the inevitable and frankly enormous question. If the measurement is correct, what has to be wrong about our understanding of the universe?
Well, if we connect this to the bigger picture, The entire framework of cosmology is now under a huge amount of stress. A co-author on the paper, Professor Dominic J. Schwartz, he frames the situation perfectly. He says if the solar system is truly moving this fast, we are forced to question fundamental assumptions about the large-scale structure of the universe.
And the research has laid out two major alternatives, two really distinct ways to interpret this excess speed. And these two hypotheses force cosmologists down two radically different theoretical roads. Let's break down the first one. We can call it the kinematic hypothesis, or hypothesis A.
Okay, so hypothesis A basically says the universe is uniform on large scales. It says the cosmological principle still holds. Therefore, the conclusion must be that our solar system's motion is genuinely, physically, far faster than we expected. The measurement is a measurement of our actual speed.
And if that's true, it means there has to be some enormous, previously undetected gravitational force that's responsible for accelerating us at this unexpected rate.
Precisely. We know about the gravitational pull of the Virgo supercluster and the local group of galaxies and our general flow toward the Shapley supercluster, what's sometimes called the Great Attractor. But all of those known forces are already factored into the expected velocity of 370 kilometers per second. To account for a speed 3.7 times greater, you need to invoke either a colossal structure far larger and more distant than anything we have currently mapped, or some kind of unusual cosmological flow we don't understand.
This really reminds me of the debate from years ago surrounding a concept called dark flow.
It's a fantastic parallel. Dark flow is this hypothesized non-random motion of entire galaxy clusters that couldn't be explained by any known gravitational attractors within the observable universe. The suggestion was that our whole local patch of the universe was being pulled towards something absolutely massive that was lurking just beyond the edge of what we can see. This new finding, if you interpret it through this kinematic lens, implies a velocity component for our solar system that is equally mysterious and non-standard.
So under hypothesis A, the standard model of the universe itself holds, but our local cosmic environment is vastly more complex than we thought. We're either missing an enormous concentration of mass, maybe a huge filament of dark matter that is currently pulling on us, or maybe the fundamental laws that govern gravity on these massive intergalactic scales need some kind of adjustment.
The big problem with hypothesis A, though, is that given how deep the LOFAR data looks, it should be measuring our velocity relative to objects so incredibly distant that any local gravitational tugs should be negligible. They should just average out. I mean, we're looking back to the relatively early universe. For a local structure to create such a massive dipole in the distant matter distribution, that structure would need to be astronomically large, potentially spanning billions of light years itself.
Which naturally leads us to the second, and I would argue far more radical alternative. Hypothesis B, the structural hypothesis.
Hypothesis B is the one that really keeps cosmologists up at night. It suggests that our model of the universe itself is fundamentally flawed. It implies that the distribution of those radio galaxies, the cosmic background of matter itself, is less uniform than we have believed.
So in this scenario, the headwind isn't just because we're moving fast, it's because the air itself is thicker in one direction.
That's a perfect way to put it. If the background itself is not uniform, then the cosmological principle is violated. The universe would be fundamentally anisotropic. It would genuinely look different in different directions at these vast scales.
And that is a deep, deep challenge to the core of modern physics. Why is the cosmological principle so crucial?
Because it underpins the mathematics we use. It dramatically simplifies the solutions to Einstein's equations of general relativity on cosmic scales. If the universe is not homogeneous and isotropic, our current standard solutions to those field equations either break down or at the very least they become vastly more complicated to solve.
And this kind of structural non-uniformity would have profound implications for our theories of the very early universe, wouldn't it? Particularly the theory of cosmic inflation.
Absolutely. The theory of inflation states that just a fraction of a second after the Big Bang, the universe underwent this period of incredible exponential expansion. And the primary purpose of inflation, cosmologically speaking, was to smooth out any initial structural irregularities. It's the mechanism that's supposed to guarantee that the universe looks the same everywhere. It's why the cosmological principle is such a good fit for the standard model.
But if hypothesis B is true, and the distant matter distribution is inherently clumpy or textured or has a preferred direction, it implies that inflation either didn't happen exactly as we thought, or that it wasn't nearly as effective at smoothing out the cosmos as our current models demand.
It raises the terrifying possibility that the cosmos has a preferred direction or an axis on the largest scales. And that's a concept that just fundamentally defies the idea of an isotropic universe. If the dipole we're measuring isn't entirely due to our motion, but is partly due to the background density of galaxies being higher in one direction and lower in another, then the entire map of the cosmic web is wrong.
So this one detection of a high-velocity dipole forces us into this incredible binary choice. Either we redefine our local kinematics with hypothesis A, which requires us to find some unseen colossal attractors, or we redefine the foundational structure of the entire universe with hypothesis B, which challenges general relativity and inflation theory itself. Neither of those options is exactly palatable for established science.
And that is the absolute beauty of this work. The study doesn't definitively choose between A and B, but it powerfully concludes that these new observational methods, using the deep reach of radio waves, advanced statistical tools, and independent cross-checks, can fundamentally reshape the questions we're even allowed to ask. They have generated definitive evidence that something is profoundly unexpected in our cosmic inventory.
And the research suggests that the next few years will be focused on increasing the precision of these background measurements, maybe using even more powerful telescopes, pushing even further out into the universe to see if this excessive dipole eventually dissipates. If it remains strong, even when looking back to the earliest possible radio galaxies, that would heavily favor the structural hypothesis, hypothesis B.
But if the dipole signal gets weaker and disappears the farther out you look, that might favor the kinematic hypothesis, hypothesis A. It would suggest the pole is more local. This journey, from a simple speed measurement to questioning the very structure of reality, is exactly why cosmology remains such a fascinating and rapidly evolving field. We started with what seemed like a technical detail, the sun's speed, and we've ended up asking whether the entire universe is uniform or if it's structured in a way that completely defies our most successful predictive model.
Let's just try to summarize this incredible journey for you, our listener. We established the baseline. The universe is supposed to be smooth, and that assumption limits our expected velocity to about 370 kilometers per second. We then used the unparalleled sensitivity of the LOFAR radio array to count billions of distant radio galaxies, measuring a faint asymmetry, a cosmic headwind caused by our motion.
And that headwind, or dipole anisotropy, was found to be a staggering 3.7 times stronger than predicted. This result was then confirmed at the rigorous 5 sigma level of certainty, which essentially rules out the possibility of it being a statistical fluke. And critically, this finding was independently verified by earlier studies that were looking at infrared quasars, guaranteeing that the signal is real and not an instrumental error.
And that forces the entire scientific community to consider two major radical paths forward. Either our solar system is being dramatically pulled much faster than expected by some colossal unseen mass concentrations, that's hypothesis A, the kinematic one, or the universe itself, at its very largest scales, is not the smooth, uniform backdrop we have always assumed it to be, which would violate the cosmological principle. That's hypothesis B, the structural one.
And the implications of hypothesis B, the idea that the underlying assumption of a uniform distribution of matter in the cosmos, which underpins decades of modern cosmological thinking, is just wrong. They're absolutely staggering to consider.
So let's leave you with this. If the matter distribution really is anisotropic, if the cosmos is clumpier or has a preferred grain or a bias in certain directions, what unexpected textures, patterns, or voids might this newly revealed anisotropy be pointing toward?
And if the universe really does have a large-scale directionality, how drastically might this non-uniformity change our maps of the cosmic web? I mean, think about it. We rely on a smooth universe to calculate how old it is, how dark energy is accelerating it, and how matter originally clumped together to form the first stars and galaxies. If the background isn't smooth, every single one of those fundamental calculations is based on a false premise. This discovery might not just tweak our cosmic history. It might require a complete rewrite of the first second of the Big Bang itself.
It's a potent reminder, isn't it, that even when we think we have the biggest answers locked down, the universe always finds a way to surprise us, pushing us toward deeper and much more challenging truths. We really encourage you to keep exploring these profound questions right alongside us.